give this talk. Today I'm gonna share with you the results of our latest experiment, which involved the study indeed of the first observation of a forced vacuum decay process, which occurs via bubble formation in a platform which is made of ferromagnetic superfluids. Throughout the talk, I would like to explain each concept which appears in the title. So what is a forced vacuum decay process and why its signature is the formation of bubbles, why we can use what are ferromagnetic superfluids and why we can use them to study this process, and then I'm gonna explain the experiment itself. So let me start with the concept of a forced vacuum. It is, in my opinion, useful to understand it from the point of view of a metastable system. Indeed, a forced vacuum shares a lot of similarities with a classical metastable system, which can be found just across a first-order phase transition. Now, a daily example is given by supercooled water, which is a particular state of water. It's a liquid phase which exists below the freezing point, and this state is very unstable. Indeed, we can observe the transition to ice, which is the natural state of the system just upon the injection of some energy. Now, this idea can be extended to the physics of fields, and the study of forced vacuum decay began after the seminal paper by Sidney Coleman, who introduced the idea and performed the first quantitative and developed the first quantitative theory, which aims at measuring, at giving an estimation of the decay rate involved in the process. So how much time does a forced vacuum to decay? And in the paper, he roughly defined a forced vacuum as a state in a field theory that is only relatively stable, because the energy density of the state is not the lowest possible. The idea gained a lot of interest because the decay of a forced vacuum has a lot of implications in the field of cosmology and high particle physics. For example, the measurement of the Higgs mass and of the top quark mass show that the potential in the Higgs field may show some kind of metastability, and in this case, our universe might lie in a metastable state, and it might decay towards the true ground state of the system, which is called the true vacuum, and in this way, it will generate a bubble of true vacuum, which will expand in the universe. Now, there are also interesting speculations regarding the birth of the universe itself. And the speculation is that the inflation period might have started as a consequence of forced vacuum decay. Now, although this is a very fascinating concept, the problem with this theory is that the timescales that are involved in this process are extremely long, and so it is very difficult to perform a measurement of the process. And the long time scale is due to the fact that the decay occurs via tunneling of the field through an energy barrier which separates the metastable state to the ground state of the system. So I would like now to just draw a brief connection with the theory of quantum tunneling. And I will start by describing by recalling what is quantum tunneling for a single particle. Now we can start, for example, taking the Lagrangian of a particle which is initially at rest in an excited state or in the local minima of a potential with a double well structure, which has a local minima and an absolute minima. Now we know that in quantum mechanics there is a finite probability for for the particle to tunnel through the energy barrier and to be localized in a different point in space, which corresponds to the global minima of the potential. And in single particle quantum mechanics, there is an analytical expression which shows that the decay rate, so the time which it takes for the particle to tunnel, depends exponentially on the area of the barrier that is separating the two minima. Now we can extend this idea to a field theory in the same way that Coleman did. So we can start by writing down the Lagrangian for a relativistic scalar field, which now contains several terms. It contains a time derivative, it contains a spatial derivative, which was not present in the previous case, and it contains a potential which now doesn't depend on space, but it depends on the state of the field itself. So if we take the same shape of the potential, now the two minima corresponds to two different values for the field, and we can identify the two minima in energy with the false vacuum and the most stable, the true vacuum. Now, the tunneling process in this case is a little bit different because the idea is that we can start from a homogeneous configuration in the field where the field is homogeneously in the false vacuum, and then at some point in time, quantum fluctuation starts to induce the tunneling through the barrier. And once the field has tunneled, it won't tunnel homogeneously because this would require too much energy. Thus, it was the most probable thing is that the field changes its value in a particular point in space and time. And this new configuration for the field is called a bubble, because for symmetry reason we expect it to be a bubble. And it is characterized by having a surface around the bubble which introduces a strong gradient, and this is because the field is now inhomogeneous, so the gradient term in the Lagrangian starts to give a non-neglectable contribution. And this surface must be taken into account if we want to understand truly the process of bubble formation. So we can look more in depth into this process. We can roughly say that the energy contained in the inner core of the bubble is given by the volume of the bubble itself times the energy density, the difference in the energy densities between the false and the true vacuum. And the energy of the bubble by itself should be let's say negative with respect to the false vacuum, because we gain energy if we turn part of the field. So we can think of it in different situations. One situation is that quantum fluctuations tends to form a bubble, and this bubble has a volume such that the energy gain in the inner part of the bubble does not compensate enough for the energy of the surface itself. The energy of the surface it's always positive by definition, and thus if we consider the two contribution, this configuration has a higher energy with respect to the initial one, so it's not an energy conserving process. The only way for the bubble to form is to conserve energy, and this configuration is what is called a resonant bubble, and it is resonant because energy conservation implies that the volume of the bubble, once it is formed, is such that it exactly compensates for the surface energy. And if this resonant bubble form at this point will be localized here, high up in the potential, so it will have a lot of potential energy, so it will naturally tend to go down the potential, and it will and this will manifest as a rapid expansion in space of the bubble. Now, the first this idea was captured by the theory that was developed by Coleman, and the idea behind his first theory is to calculate the the decay rate, so the time that it takes for the bubble to nucleate. And to develop the theory, consider that the bubble, once it nucleates, the nucleation must be a stochastic process. It must be random in space and time. And what he wanted to calculate was the transition from a false vacuum state to a bubble state. Now, it turns out that this calculation is impossible unless one performs a trick, which is to switch to imaginary time or to Euclidean time. And in this case, by going in Euclidean time, the problem is much different. It's not the one of a false vacuum, of a field that has to tunnel through the barrier, but it is the problem is the one of a field which is originally in a state of a tilted potential, and so it is high up in energy in this tilted potential, and thus it has the possibility to roll down the potential, reach what is called a turning point, and then bounce back. Now, this trajectory, which is the solution of the Euler-Lagrange equation in this tilted potential or in Euclidean time, is now called an instanton. And what Coleman showed is that if one is able to calculate the shape of the instanton, then the decay rate has a very simple expression. It's just given by a prefactor times an exponential dependence on the action of the Lagrangian, where the action is calculated on the instanton on the instanton solution. Now, this is the first theory that was developed, and it was developed in the zero temperature case. Right after the paper by Coleman, there has been a lot of research to extend the theory to the finite temperature case. And the finite temperature is important to be taken into account for two reasons. The first one is because in real systems, we always have a temperature. And the second reason is that the potential itself might depend on the temperature. Actually, it was shown that the inclusion of a temperature is not very difficult. Actually, we can have several, let's say, three kinds of processes. For temperature which is very low, we can completely neglect the role of temperature, and we are left with the zero temperature case. Then we can have a situation in which the temperature is sufficiently high to move the field up to some point in the potential barrier from which the field can tunnel, and thus the role of the temperature is to, what we expect is that the presence of thermal fluctuations will change the tunneling rate because the shape of the barrier changes. And then there is a fourth situation where temperature is so high that the field can be moved up to the EL, up to the potential, and then it just rolls down, which is somehow a classical scenario. And if we take into account this situation, what it turns out is that the decay rate can be modified. It has this simple form where we basically substituted the time integration with a Boltzmann factor, which depends on temperature. And the action is now the three-dimensional integral in space, which directly gives the energy of the barrier. And a nice thing about this formula is that it should be now clear that the energy barrier that the field has to overcome does not include only the potential, the regional potential itself, but it includes also the kinetic contribution, so the contribution of the surface of the bubble. With this, I would like to conclude. This was just a short summary of short introduction to the theory. And the problem now, the problem with this process is that there has been no experimental verification because it was originally studied in the cosmological and high particle scenario, where the energy scales involved are too high, or simply where we don't have any parameters that we can tune to accelerate the decay rate. So there has been a lot of research to find a system in which we can explore this process. And the system which one should find is a system which has either a field-dependent double well potential or a first-order phase transition, which depends on the field itself. It should have a spatial extension, and it should be tunable in such a way that we can tune the decay rate and verify the theory. And to my knowledge, there has been some research involving some proposals which aims at using spin chains and ferromagnetic system. This is because ferromagnetic system already has features a natural first order phase transition, so we can exploit this scenario. But it has these systems as the small caveat that are discretized, so it might be the physics of the decay might be a little bit different. And on the other end, there has been a lot of proposals which aims at use ultracold atoms with an engineered double well potential. And actually, the system that we have in our laboratory, that is the one we use for the experiment, is kind of in the middle between the two, because it has a ferromagnetic order parameter, and the order parameter is also it has also superfluid character. That's because our system is composed of Bose-Einstein condensates, which we know to support superfluidity. So let's. So I would like now to describe this system. Now, the system that we have in the lab is a mixture of Bose-Einstein condensates of sodium atoms. In particular, this is the ground state, the electronic ground state structure of sodium atoms. What we do is to target to prepare the atoms in this state here, and to couple this state with its stretch state with a coherent radiation. And the coherent radiation is very important because it is what gives the ferromagnetic behavior to the system. And the radiation has a radio frequency and the tuning which we can tune from the atomic resonance. Now, the dynamics of the system is described by two gross Pitaevskii equations. We have two order parameters, one for each spin states. I'm starting calling these states spin down and spin up to better draw an analogy with magnetic materials. Now, each order parameter evolves accordingly to its gross Pitaevskii equation. So we have two different mean field energies, which depends on the coupling constant. The two equations are coupled via interspecies coupling constant, which arises from interactions between atoms from the two different states. And then we have the coupling term, whose role at the first order is to interconvert particles from one state to the other. Now, for the specific choice of these states, we have these are the values of the scattering lengths, which directly gives the coupling constants. And for this value of the scattering lengths, we have a mixture which is called immiscible. Now, this is a photo, an absorption images photo of the two states, the spin down state and the spin up state. And what we see is that the mixture is also characterized by a phase separated behavior because indeed it is immiscible. Now, in order to better understand the physics of this system, it is useful to introduce the normal modes of the system, which are the modes that diagonalize the Hamiltonian. In the two modes, I will call them density mode and spin mode because they correspond to in-phase oscillation of the two components or out-of-phase oscillations. Now, for what concerns our experiment, we can neglect density modes because they are not affected because we are not interested in in the density, and we will just focus on the spin modes. And it is useful now to introduce what we call the typical energy scale, or the spin interaction energy, which is the energy scale of these spin modes. It is an analogy with the density chemical potential, and this spin interaction energy Kn is given by this combination of the coupling constants, and it directly coupled to the atomic density. So this coupling gives us a way to tune the interaction energy. Now, to better understand the behavior of the system, we can also introduce two variables describing the internal spin state, and these variables are the relative magnetization, which is the difference between the two atomic density, and the relative phase, which is the difference between the two phases of the order parameters. And with these variables, we can write down the energy in local density approximation. Here we neglect the phase because we are interested in working in the ground state of the system, and the ground state of this system is found for a vanishing relative phase. So we see that the energy as a function of Z is determined by different combinations of three parameters. Particularly, we have the spin interaction energy here. We have the Rabi coupling, and we have also the detuning term, which actually is a combination of the detuning term, the detuning from atomic resonance, which we can tune by changing the bias field, and also we have an additional term which couples again to the density, which depends on the imbalance between the intraspecies coupling constant. Now, what is interesting is that this energy functional is very close to the Hamiltonian of a transverse field Ising model, or quantum Ising model. Indeed, at the mean field level, the two systems shares the same universality class. And this is an important element because being in the same class of the transverse field Ising model, it means that we have access to two quantum phase transition. A second order quantum phase transition, which we can explore with our first tuning knob, which is the ratio between the Rabi frequency and the spin interaction energy, and the first order quantum phase transition, which can be tuned by varying the detuning. Now, for what concerns the second order quantum phase transition, if we can compute the ground state magnetization of the system, and we found that we have a bifurcation. The bifurcation occurs when the Rabi frequency is tuned to be lower than the spin interaction energy, and the bifurcation corresponds to having two degenerate ground states for the magnetization, a positive one and a negative one, which corresponds to having, if we calculate the energy of the system, to having a symmetric double well potential. Now, starting from the ferromagnetic side, we have also access to a first order quantum phase transition, and this can be explored by varying the tuning. What is shown here is again the ground state magnetization as a function of the detuning, and what we see is a sort of hysteresis cycle of the magnetization. An important thing about having an hysteresis cycle is that we can have two situations here and here, where the detuning and the magnetizations are opposite in sign. And if this occurs, one of the two, we can have a system which is characterized by whose energy profile is characterized by having a tilted double well profile, and it may lie in the metastable region, which would correspond to this side of the hysteresis cycle, or this side here. And the hysteresis cycle actually has a boundary up to a critical detuning, where we enter what is called a saturated ferromagnetic region. Basically, the metastable state just disappears. But the important thing here is that with this system, we have naturally first order phase transition with a double well that we can tune at will through delta and through the detuning and the Rabi frequency. Now, to realize this system in the lab, we realize Bose-Einstein condensates of sodium. We condense more or less 1 million atoms at a temperature of 1 microkelvin, which is a non-neglectable temperature for our parameters. The condensates are produced in a single optical dipole trap. We produce one condensate for experimental shot, and we image from the top, so we can have access to the actual dynamics. We have a spin selective imaging technique, so we can distinguish between the two spin states. Now, on top of this, we have magnetic coils which produce a highly stable bias field, which we use to tune the resonant condition, and thus it can be used to tune the detuning. And we also have antennas to drive the microwave transitions to populate the different hyperfine states. Now, a nice thing of having a harmonic potential is that the density and thus the spin interaction energy is higher in the center of the trap. So if we can go to enough low values of the Rabi coupling, still maintaining the coherence of the radiation, we can engineer different magnetic phases in the same sample. Now, the most important ones are the ferromagnetic region in the center of the trap, because it's where we can, it is in this region that we can study the force vacuum decay process. And on top of having a ferromagnetic region, we also have paramagnetic regions on the side where the density goes to 0, and thus we enter a paramagnetic regime. Now, as I said, what we need is to lower the Rabi frequency to a low enough value so that the system is ferromagnetic. Now, if we estimate the strength of the Rabi frequency, it has to be, if we estimate the strength of the spin interaction energy, this is on the order of 1 kHz. So it means that the Rabi frequency must be much less than 1 kHz. And in particular, if we want to retain the resonance condition, the noise on resonance must be contained. And it must be contained at the microgauss level. To accomplish this task, our vacuum chamber is surrounded by a magnetic shield composed of 4 layers of metal. And we've previously demonstrated that with these layers, we can achieve suppression of the fluctuations by 6 orders of magnitudes. In particular, we have measured the noise at the level of 2 to 4 microgauss. And this is crucial to 2 points. The first point is that we can, with this value, we can retain the resonance condition. And the second one is that we can, we have very fine tunability on this double well potential structure because it directly depends on the detuning. With this, we can start discussing the experiment that we have performed. So the main idea in our study is that we can engineer a homogeneous state. We can, let's say, prepare homogeneously our condensed cloud in a false vacuum state. And we do this by creating the internal double well structure in such a way that the magnetization is uniformly positive throughout the sample. And with this we have the field that acts as a simulator is the magnetization itself. Now, in our system, we can have, in principle, both quantum and thermal fluctuations, which might drive the decay. And as we've seen before, only some bubbles, if they form, can form. And for us, these bubbles are expected to be in one-dimensional. because of the geometry of the sample. And they should be protected by two domain walls, which interpolates between region of different magnetization. And the bubble itself is a bubble with negative magnetization, so all the spins in the inner part of the bubble should point downwards. Now, once the bubble is formed, we expect it again to expand in the sample. Now, this is the idea that we have in mind. We have also built created an instanton theory for this kind of system. In particular, we started from the Lagrangian, which is a function of z of the magnetization and of the relative phase. And we've made a few assumptions. At first, we have introduced the temperature, so we have neglected the temporal derivative. And we introduced this beta parameter, which is a kind of spin temperature of the system. The second thing is that we have neglected any relative phase contribution, in particular any gradient of the relative phase. This is because the ground state of the system, so this double well structure occurs only for phi equals 0. And then we are left with these two elements, which are the gradient which comes from the domain walls. And this gradient actually stems from the superfluid behavior. If our gas were ferromagnetic but not superfluid, we wouldn't have any gradient contribution. And so we have the gradient contribution and the potential energy, which adds up to form the energy of the barrier. Now we can study the shape of the energy of the barrier as a function of the control parameters. It turns out that in one dimension we can simplify the calculation of the energy barrier by changing the integral from space to the field itself. And in this case, we are able to numerically calculate this energy barrier, and it is the value of the energy barrier is shown here in this as a color plot. Yellow means a stronger energy barrier, and also it means a much larger decay time. So in this diagram, in this diagram, we have on the horizontal axis the Rabi coupling, and on the vertical axis we have the tuning. Now there are two regimes in which we can work to have a straightforward comparison with theory, and these are called the thin wall approximation and the small barrier approximation. Now, the thin wall approximation corresponds to having a slightly double well, so we can encounter this situation if we set the detuning to be very small, and it basically corresponds to move along this line. Now, along this line, the action or the energy of the barrier depends strongly on the Rabi frequency. And as a caveat of working in this regime, the height of the barrier is very high. Then the area of the barrier is very high. So we expect that the decay rate exceeds the coherence time of our experiment. So this is a regime in which we actually can, at the moment, we cannot perform any measurement. Now, the other regime, which is the one we have used, in which we have performed the experiment, is the regime of small barrier approximation, where we basically move along the line separating the ferromagnetic region to the saturated ferromagnetic region, so very close to the critical detuning. Now, in this regime, the double well results to be highly tilted. The difference in the two vacua can be tuned very efficiently with the detuning, and we have small dependence on the Rabi frequency. So as I said, this is the regime which we have explored in our experiment. So we can finally come to the experimental protocol. We started our experiment with a cloud which is fully prepared in a state with positive magnetization. We do it by, we prepare the state with a positive magnetization by turning on the coupling with a positive detuning, which is much stronger than the density-dependent detuning that we have in the center of the trap. And this ensures that the cloud is in the ground state and it is fully polarized. Now, what I've shown here are different energy profiles calculated in different regions. So this one would be the energy profile corresponding to the center, and these ones corresponds to the tails. We see that on the tails, indeed, we have a paramagnetic region, and when we move to the center, we start having a double well potential, and actually the shape of the double well depends also on the position, also because of the density dependent tuning. So the protocol that we applied is quite straightforward. Once the state is initialized, we perform an adiabatic ramp in the detuning, so we lower it up to a point where in the center of the cloud, the tuning, the effective detuning as seen by the atoms has an opposite sign with respect to the magnetization. So we prepare here a metastable state. And then at this point, we just wait and gather several absorption images of the issue state. So at t equals 0, the magnetization is blue, meaning that the state is fully positive. And at some point, when the field tunnels in the central region of the cloud, we witness the formation of a bubble. This bubble has, as expected, two domain walls, and it is one-dimensional, as we expect from the geometry of our system. And if we wait a little bit longer, what we observe is that the true vacuum region has expanded in the sample as soon as other parts of the system tunnels towards the ground state. So this is a confirmation that what we see is the spontaneous nucleation of bubbles. What we wanted was to perform some quantitative measurement. And the way we have to perform quantitative measurement in order to avoid, to overcome the problem that our imaging is destructive, is to take a statistical measurement of the occurrence probability of the bubble. And on top of this, we also performed numerical simulations to have better access at the dynamics of the formation of the bubble. Now, for the experiment, what I reported here are the values for the integrated magnetization as a function of space and as a function of time. Each window here collects shots taken at the same time. And what we see is that at early times, there is no transition towards the ground state, or at least we only see one bubble out of 10 forming. Now, as long as we wait a little bit longer, the transition occurs much more often. And at late times, when we take a photo, we always see a bubble which has formed and expanded. So what we did to obtain an observable was to quantify the statistical probability of seeing one bubble, and we quantify it just by counting the bubbles at each time. What we obtained is what we measured was an exponential increase in the probability of seeing a bubble up to a point in which this probability saturates, which is once we have passed the typical decay time. And from the simulations, we can have more information because the simulation allows us to track in real time the evolution of the bubble. So we see that indeed the bubble forms not only randomly both in time and in space. In time because we see different time of appearance of the bubble, and in space because we see different initial position. And once the bubble is formed, it just expands in the samples, and then up to a point in which it is bounded that it can't expand anymore. Now, what this gives already a way to quantify the decay rate, so the time that it occurs to observe a bubble. But what we used was a more modern indicator, which is called the force vacuum fraction. Now, the force vacuum fraction basically keeps into is an estimator of how much how fast the force vacuum drifts towards the true vacuum, and it is obtained, and we obtain it by it is an average quantity, and we obtain it by averaging the experimental shot taken at the same the measurement taken at the same time. Now you see here the experiment, and here on the right the simulation, both averaged for two different values of the tuning. So we have a strongly tilted double well here, and a slightly less tilted double well on top. Now, the first thing that we see is that the bubble occurs at different times. As we expect, we have some kind of control with our tuning parameter. Now, if we calculate the force vacuum fraction using this formula, we obtain the data points that are shown here for the experiment and for the simulation. And in both, what we see is indeed that after an initial, after the system is at rest at the beginning, we have an exponential decay towards the ground state. And from this decay, what we can do is to extract the slope, and the slope is actually a good measurement for the decay time. Now, the decay time is plotted here for a particular realization. This is measured for Rabi frequency at 300 Hz. And what we see is that we have a strong enhancement of the decay time as a function of the control parameter. The control parameter for us is the distance from the critical detuning. So we see that when we are very close, the decay time is very small. It is on the order of some milliseconds, and it increases more than exponentially when we go far from the critical point. And it actually it covers it changes a lot, because it goes from some millisecond to some 100 milliseconds. So the last thing that we did was to gather different data sets. So as we have two control parameters, we change both. We change both the tuning and the Rabi frequency. And we repeated this procedure for each dataset to extract each point here. And each experimental point was validated with numerical simulations and also with instanton theory. Indeed, as explained before, we had in this regime which we are working with, we have we found an analytical expression for the energy barrier, which we used to fit our data. And with this, we find a great agreement between theory, simulation, and experiment. And the last thing that I would like to stress is that we have in this kind of process, we have a very strong sensitivity of the decay rate for a very small variation in the tuning parameter. Indeed, we varied together with dataset. We varied the tuning of only some of less than 100 microgauss, and this is allowed by our experimental setup. And with this, I would like to conclude. So to recap, we have provided a first strong observation of thermally triggered for the first vacuum decay. Our observation is confirmed by numerical simulation and those by instanton theory. And there are a few research lines that we would like to explore we're exploring actually. One is the role of temperature effects on the first vacuum decay rate, which we expect if we are trying to finely tune the temperature without affecting the other parameters. We expect the decay rate to be suppressed for vanishing temperature. The other one is to look at what happens if we inject a nucleation seed. We can do it via phasing print. And what we expect, there are two things. The first thing is that we should have an acceleration of the decay rate, and this is an analogy of having black holes in the early universe. There has been a few papers also trying to simulate with cold atoms numerically. And the other idea is that we can study, we could create deterministically create bubbles in this way, and so we can better study the expansion dynamics. And at last, we would like to extend. This is a major improvement. We would like to extend the experimental platform to realize a disk so that we can study collisions between two-dimensional bubbles. With this, I would like to conclude and thank all the experimental group and the theory support from both Trento and from Newcastle.
Thank you very much. It was very interesting. Questions, please. Just go ahead and unmute yourself if you have a question. While we wait, okay, Mark, please.
Yes, thank you very much. Very, very interesting talk. Very exciting work. So, a couple of questions, if I may. Roughly, how many atoms are partaking in the forming the critical bubble?
So we have a density which is more or less 4,000 atoms per micron. Linear density integrated, and we estimated actually the smallest bubble is below the experimental resolution of the imaging system. We estimated it from numerical simulations, and it should be around. Actually, I have a plot of the numerical simulations. Of course, it depends on the tuning. But it should be around 1 micron, half a micron.
So, so the smallest is a few thousand, and then what was the largest?
I don't remember. So the largest is very difficult to discern because of the stochasticity of the process. We are not able to see. We're not able to understand which is the largest bubble for, or at least we don't have enough statistics to say that for small detuning that is a certain shape is the minimum shape. It's a measurement that we're trying to do to perform actually.
Okay, thanks a lot. Okay, can I have a second question?
Yes, of course.
So you showed that you got a nice fit with the thermal activation, but
yes.
did you try vacuum decay, the vacuum version, and get a bad fit?
Yes, yes, we did, and it doesn't fit the theory. Also, it doesn't fit the the data very well, and also it would be very incorrect for from a principle, from the point of view of neglecting the temperature, because the condensate fraction in that we have in the lab is about 30% of the whole gas. So we know that there is a high contribution of temperature.
Okay, thanks.
Yeah, you're welcome.
I might actually continue from there. So you had this slides towards the end of the presentation about the two simple cases in theory, one of which you've been discussing, and the other one which is not accessible in cold atom experiment, at least as of now. Did I understand correctly that basically the scenario on the left is one where the potential difference or the energy difference, bulk energy difference between the two states is very small as compared with the barrier, and so therefore the lifetime of the metastable state is very long. Is that right?
Exactly, that's the scenario.
Right. Okay. Because this is now, okay, there are people who understand theory better than I do, like Mark probably in the call. But I mean, as I understand, this is closer to the scenario in helium-3. So I was going to grab this opportunity and advertise cheekily our own work a little bit. So in helium-3, there is actually a long history of experiments of looking at how the first order phase transition between the A phase and the B phase takes place in 3 dimensions. And the outcome so far in published literature is that it does not follow this homogeneous nucleation theory, or if you like, thermal fluctuation driven transition whatsoever. And so while that remains an open problem, there's a large body of work around there, for example, about speculations of what possible other effects might be important. Now, I'm not saying that these are necessarily relevant to what you're doing, but I'm just wanted to grab this chance of mentioning that this line of work exists, and we're actually actively investigating it with some of the people here today.
Yeah, that would be very interesting, I think, to have different platforms to have to access different regimes, and also to provide different numerical experimental values for the decay rate and the actual prefactors.
Yeah, well,
as that.
With helium-3, obviously you observe this transition. They actually occur much more often than what should be the case. And then, well, it has been shown that, for example, by imposing a lot of radiation, like either cosmic rays or even bringing like some radioactive material close to your container, one can impose the transition. What is not so well understood is what happens if you remove this kind of external influence, and that's the ultimate goal of the project, which is ongoing, although might be very difficult to access. I mean, the main point is that if the homogeneous theory is correct, and one manages to remove all external sources, then it will take, like, you know, more than the lifetime of the universe to trigger the transition, while in a practical experiment you actually do see these every now and then, so it's not that it takes forever.
I see. Yeah.
Do we have any other questions? Well, while people are still thinking, we're coming to 5 p.m, so I will just briefly update you on what's going to happen next. So the next webinar is going to be given in 2 weeks' time, on the 17th of April. This is a Wednesday, so an unusual day for us. It's not on a Tuesday. If we do not have any further questions at this time, then I would like to thank the speaker once again. It was a pleasure having you presenting to us.
Thank you very much.
And also I'd like to thank everybody who joined the call today on the webinar, and I'll see you in 2 weeks' time.
Thank you. See you.